Hey everyone, and welcome to this explainer. Today, we're going on a tour of a massive, completely invisible metropolis. You see, enterprise data doesn't just, float around in some dark, empty void. It actually lives, breathes, and operates in highly distinct architectural structures built for very specific purposes. So let's step right into the data city. Okay, let's dive into this. We hear it all the time, right? Data is the new oil, or we're in the information age. But honestly, where does the internet actually physically put its massive memories? How exactly does a global bank instantly know your checking balance while simultaneously analyzing a decade of complex market trends? Well, the secret is all in the architecture. Before we start visiting our three main city districts, let's quickly define what we even mean by database architecture. Basically, it's the fundamental structural design, the storage mechanisms, and the operational logic that dictate exactly how data is managed, scaled, and retrieved. Think about a physical city. You've got residential zones, industrial parks, and financial districts, and each one operates with totally different rules and infrastructure, right? Well, our data city is exactly the same. It has distinct systems built specifically to handle different types of chaos and order. Section 1. NoSQL, the Agile Market. Think of NoSQL as the city's completely chaotic, fast-paced, and infinitely expandable open-air market. Now, for decades, we relied heavily on traditional relational databases, the RDBMS. You can picture those as incredibly strict corporate office buildings where every single piece of data had to fit perfectly into rigid, predefined tables, rows, and columns. But NoSQL? It totally breaks all those rules. It uses dynamic documents, usually in a format called JSON or BSON, and the best part? It's completely schemaless. Imagine our open air market. One vendor might be selling apples, and the guy right next to him is selling electronics. In NoSQL, documents sitting in the exact same collection can literally have entirely different fields. You just don't need a rigid blueprint to set up shop here. This amazing flexibility actually solves a massive architectural problem, scaling. Traditional relational databases have to scale vertically. What does that mean? Well, if you need more computing power, you literally have to upgrade your one single massive server machine with more RAM and better CPUs. It's exactly like trying to build a taller and taller skyscraper. Eventually, the laws of physics and, let's be real, your IT budget are going to hit a very hard ceiling. And this brilliantly illustrates the NoSQL approach, which is horizontal scaling, or sharding. Instead of trying to build one impossibly tall skyscraper, NoSQL simply expands the market by adding more tents. It distributes your data across a cluster of cheap, everyday commodity servers. If your website traffic suddenly doubles overnight, you don't rebuild the whole thing. You literally just add more servers to the network. It's an architecture purposefully designed to scale out endlessly. Now, within this massive market, you'll find different types of stalls. Take MongoDB, for example. It's a document-oriented database that uses a single master setup, which is absolutely perfect for agile web development. On the flip side, you have Apache Cassandra. That's a wide-column store with a masterless peer-to-peer architecture where every single node is equal. It's purpose-built to handle massive, nonstop data streams, like pinging millions of IoT sensors. But here's the thing. They both share a core philosophy, known as the base model. They essentially trade strict, absolute perfection in order to be basically available, have a soft state, and achieve eventual consistency. Basically, they prioritize keeping the market open and moving super fast. Section 2. Data Warehouse, the Historical Library. So, when the chaotic daily market finally closes, we need to make some sense of everything that was sold over the last, say, 10 years. That's when we head over to the data warehouse, the city's quiet, meticulously organized historical library. Now, a data warehouse is fundamentally different from your everyday operational database. According to data pioneer W.H. Inman, it has four foundational traits. First, it's subject-oriented, meaning it's organized around broad business concepts like sales rather than individual checkout receipts. Second, it's integrated, so it merges all that messy, chaotic data from all over the city into one clean, uniform format. Third, it's time-variant, mapping everything to a specific historical date. And finally, it is non-volatile. Once a piece of data goes into this warehouse, it's strictly read-only. We never delete history here, we literally just add new volumes to the shelves. To actually navigate this massive library, we use something called OLAP, or Online Analytical Processing. If your operational databases are built for super quick, single-row writes, like ringing up one single customer at the register, OLAP is the library's advanced indexing system. It's heavily designed for complex, read-heavy analytical queries that can scan millions of rows in seconds to find long-term trends.
Now, what's really interesting about this slide is seeing how we actually organize the bookshelves in this massive library. The two main architectural designs here are the star schema and the snowflake schema. A star schema has a central fact table holding your core numbers, which is then surrounded by dimension tables holding your descriptive text. It's what we call denormalized, meaning there's absolutely some duplicate data in there, but because it requires fewer joins, your query speeds are incredibly fast. The snowflake schema, on the other hand, breaks those dimension tables down even further into normalized subtables. This saves a ton of storage space because there's absolutely zero redundancy, but it requires much more complex joins, which can really slow down your reading speed. It's a classic architectural trade-off.
And OLAP itself actually comes in a couple of different architectural flavors. MOLAP stores data in proprietary multidimensional arrays, often called cubes. It literally pre-calculates the answers before you even ask the question, offering lightning-fast speeds. But it can kind of hit a wall when you start dealing with super granular raw data. Then you have ROLAP, or relational OLAP. This one skips the cubes entirely and translates your questions dynamically into complex SQL queries against standard relational tables. It's highly scalable for sure, but it can be slightly slower because it's forced to do all the math on the fly.
Section 3. Data mining the detective agency. Now, having a massive library full of books doesn't mean you actually understand what's written inside them, right? And that brings us to data mining. These are the city's detectives. They actively investigate to uncover hidden patterns using a framework called Knowledge Discovery in Databases, or KDD. Think of this as their standard operating procedure. Step 1, they clean and integrate the messy clues. Step 2, they select and transform the relevant data. Step 3, they execute specialized mining algorithms. Step 4, they evaluate the patterns to make sure they aren't just random coincidences. And finally, Step 5, they present actionable knowledge to the decision makers. But here is a truly surprising fact about being a data detective. You might think it's all about running glamorous, futuristic AI algorithms all day long. In reality, a massive 80% of their time is spent literally just cleaning up the data. This is known as the ETL phase: extract, transform, and load. Real-world data is incredibly noisy, totally corrupted, and full of blank spaces. And the absolute golden rule of data science is pretty simple. If you feed absolute garbage into a brilliant machine learning algorithm, you are just going to get incredibly precise garbage predictions right back out. Once the data is finally clean and ready to go, the detectives use two main types of algorithms. Predictive algorithms, like classification or regression, look at historical training data with known outcomes to forecast the future. It's kind of like profiling a known suspect to predict their very next move. Descriptive algorithms, on the other hand, are all about exploring the unknown. Using techniques like clustering or association, they find hidden groupings in completely unlabeled data. They aren't forecasting a specific event, they're actually revealing the hidden structure of the city itself. And guys, this complex math solves incredibly real, everyday problems. Banks use classification algorithms to instantly detect fraud, mapping your normal behavior and flagging bizarre anomalies the second they happen. Hospitals use decision trees on electronic health records to predict early risk factors for chronic diseases. And retailers? They use association rules, like the famous a priori algorithm, for market basket analysis. That is literally the math that figured out that people who buy diapers on a Friday night are also highly likely to buy a six-pack of beer. Section 4. Ecosystem. Putting it together. Let's see how this all builds together. We've toured the chaotic market, the quiet library, and the sharp detective agency. But the true magic happens when we view these distinct architectures as one fully integrated ecosystem. Here is your data city at a glance. NoSQL is your agile market. Its primary purpose is handling high-volume, dynamic transactional data using schemaless documents that scale horizontally. The data warehouse is your historical library. It takes the output from that market, cleans it up, and stores it in highly structured dimensional schemas designed specifically for read-heavy, long-term trend reporting. And finally, data mining acts as the detective agency. It sits right on top of the library, deploying complex mathematical models and algorithms to discover hidden patterns and make proactive predictions. They are completely different architectures, but here's the catch. They rely on each other entirely. You absolutely cannot mine patterns without a warehouse of history, and you can't build a history without those agile databases capturing the present moment. So as we wrap up this explainer, I want to leave you with a thought to ponder about your own data ecosystems. Considering the immense power of these interconnected architectures, how much hidden knowledge is sitting completely undiscovered in your own company's servers right now? Thanks so much for joining me on this tour of the Data City.